All right, we're going to start now. We we are starting the course Control Engineering and Automation. If and when you can see my screen, let me know. How do I put this so I don't interfere? Okay. Can you see my screen?
Yes, sir.
Okay, lovely. Good. So this is EME 413. It's Control Engineering and Automation, right? It's a 3 credit load course. So they have made you guys very unfortunate. They put you in my hand for heavy, heavy courses. Machine design, 4 credit loads. Control engineering, automation, 3 credit loads. So, you know, yeah, in my hand. But for this course, we'll be 3 taking it. Myself, Engineer Victor Chigbenda, and Engineer Benjamin Amwa. Okay. Um, the course synopsis we we have elements of process control, servo systems, transfer functions and analysis, transients and frequency responses. We will look at systems stability, body plots, Nichols plots, Nyquist charts. All of these, they are compensating techniques. Okay. When we begin to explore the concept, we would understand, and then we'll handle elements of nonlinear systems, control systems design, and look at the industrial applications. And the three of us, I'll certainly take elements, I'll introduce the caustic elements of process control and control systems. We'll look at servo systems, and then we'll look at transfer functions analysis. These are the foundations to control engineering and automation. Then engineer Amoa and Achibuna will come and take the rest of the topics. Depending on how comfortable they are, I've already discussed, put it on our charts. This is how it will be. But if Amoa would prefer to come much later, then he will exchange topics with Victor. So just once I finish, whoever comes next, excuse me, um, will be the next person to check it. Now, a few things very, very quickly. Control engineering and automation is a very calculative course. Okay, there's a lot of mathematics in it. In fact, it's at some points it would be as though you were doing just mathematics. But I would want you not to lose sight of the application. Usually, as we teach you the principles and we take you through why the calculations are done and how they are done, it's always important for us to link all of that to their industrial application. That's why you see on the synopsis, hopefully we get there. If we don't, it's still fine, right? And so um, it's important not to lose sight of where we're going and the overall concept of what control engineering is all about, as I will explain very, very shortly, right? So um, pay attention as it is with maths. If you miss the foundations, you will struggle with further topics and further actions in your calculation. So pay attention at the beginning, get the foundation properly so that you are not struggling much later. Now, we could approach this in such a way that you can just cram everything and come and pass and go away. I had an A in control engineering and automation when I did this many, many years back, sometime maybe 2006, 2007, thereabouts. And, I was feeling like, yeah, I know control engineering and automation. But by the time I went for my master's, I did my master's in mechatronics. By the time I went for my master's, and we now started doing proper control. Boy, I knew that, man. I, I knew nothing at all about control. And the A I got was as if it was not, it was as if it was an F. So I had to work extra hard. I had to study afresh. I had to go through so many things, things that we never touched. Indeed, indeed, our cost structure is flawed because control is a massive cost. There are two courses that, or two aspects of mechanical engineering that we do not pay very much attention to. One of them is this control engineering and automation we're talking about. In fact, it's a course on itself. You can enroll for an undergraduate degree and study control engineering and automation for 5 years. That's what you guys are doing in one course in one semester because you don't do control again. This is the only time you do control, automation, and engineering. So we are just going to scratch the surface of what this is, right? Um, but even at that, we want you to pay very good attention. The other cause that we don't pay attention to in Justun is vibrations. We don't do vibrations a lot, and vibrations are very foundational. It's a foundational aspect of mechanical engineering. You guys, when you come to final year, you will have vibrations as an elective system dynamics and acoustics. That's where you deal with vibrations. You have a little bit of vibrations in, I think, it's either theory of machine, no, it's mechanics of machines. You have a little bit of vibrations there, and then you have it as an elective in 500 level, but that's all. Yet, it's also a very, very important aspect of mechanical engineering. So just to say that you should pay attention, you should kindly, you know, um, focus and gain understanding as much as possible, right? And then we move on. Hopefully, I would make this video available to you guys. I'll probably upload it to my YouTube and give you guys the link so you can follow it. All right, that being said, so this class, we will not go too far. We will begin with elements of process control. That's the introductory part. We'll look at what control engineering really is all about. And then we'll start looking at the concepts, the basic concepts of control systems, those concepts that form the elements, okay, of what process control is all about. We will not go too far today because I was rushing to get these slides up since I wouldn't be in class in person, but I couldn't put them together. So we'll go as far as my slides are ready for this week, and then we'll continue the next week. After the class, we'll discuss very quickly and see whether this online mode of lectures are suitable for you guys or whether we should strive to find the classroom. I know you have agreed and you're working on the classroom in class. If that, I mean, in school, if that gets ready, then we will resume in person. But if not, we will assess at the end of this class whether this online thing is good. Plus the fact that you also have videos that you can always go back to thereafter. Okay, so having said that, let's begin on what control engineering is. What is control engineering? So basically, uh, control engineering is about designing, is that endeavor, engineering endeavor that focuses on the design, the analysis, and the optimization of control systems, all right? The design, the analysis, and the optimization of control systems. And we have control systems everywhere in our lives today. Before, you had majorly control systems limited to industrial settings and all of that. Then gradually they began to become domesticated. Now control systems are everywhere, right? Everywhere. Almost every product has some form of control. Now, okay, if you look at your air conditioner, it is a control system, right? it imparts on the temperature in a given space. It controls the temperature in a given space. So a control system consists of many systems, subsystems that have been put together, or processes that have been, arranged to interact one with another for the purpose of obtaining a desired output or a desired performance from the system. Okay? And you would usually have an input to the control system, and then the control system now works on. For example, when you want to control the temperature in a room. So before air conditioners came, right, we had fans. Okay, we had what? Fans. You're feeling hot, you turn on your fan. Okay. But what the fan did was it did not necessarily control the temperature. It did not control the properties of the air. Because air conditioners do not only control temperature. Okay. What your fans did was to create a draft, movement of air. Okay, because our body systems are designed in such a way that when we are very hot, okay, we sweat, we sweat, and so the heat of vaporization of sweat, when the sweat forms on the body, the heat that we are feeling and from the heat from the body will cause it to vaporize. So in vaporizing, in changing state from liquid to gaseous, it collects the heat from our body. Okay, that's the mechanism of cooling that God has designed for our body system. Okay, so you will discover that what a fan will do is to now create a draft air that flows over your body, and as it flows, it enhances the evaporation of the sweat on your body. Okay. And as the air blows over your body, and those sweats, as it were, vaporize and move away from your body, you feel cooler and cooler, as the case may be. But the temperature of the air is not changed per se significantly. All right. But when you have an air conditioner, what it does is it imparts what's the word now? It directly tampers with, it changes the temperature of the room. In addition to changing that, it also controls the humidity, right? Because when you stay in a place that is very cold but dry, your body doesn't feel comfortable. It has very adverse effects. Your lips crack, your skin dries up, and all of that. So the air that is suitable for human beings should be, it should be cool, but also um, humid to some point. Okay, not densely humid, because when it becomes densely humid, it becomes uncomfortable as well. So your air conditioner system now has an input. So you will use your remote control and instruct. That's the input you are making. You set the temperature. You are telling um your air conditioner that I want this room to be cooled to a temperature of, let's say, 19 degrees Celsius, right? And so the air conditioner has sensors that measure the temperature of the air in the room. So what it does is it takes the air in the room, passes it through its system, and delivers, or rather takes air from outside. So there's a draft that is created, takes air, cools the air, brings that into the room, extracts the one in the room, and you have that cycle that continues. And when the temperature of the room gets to the desired temperature, it turns off its uh, its system, the condenser, right, that controls the cooling of the air. That's how an AC works. That is a control system. Okay. So you have your system, and we will define what a system is. We'll define what a control system is very shortly. You have your system. There is an input that comes into the system, as you can see in this diagram, right? Your input, it goes into the control system. Your control system understands that that's what you desire. So it works on that input and it produces an output. Okay. I've used the air conditioner as an example, but there are several other examples, right? And we'll see them when we come to um, dealing with transfer functions. We'll look at transfer functions of different systems in different mechanical systems. And then we'll handle a little bit of electrical systems, though we won't go in depth with that. So let's look at some basic concepts. And this is where we'll just deal with basic concepts of control systems for today before we move on. Okay. Control is very, very, very massive. Before I start defining them, I just give you one example. Part of what we did, by the time I went and started doing my master's, I appreciated God, right? God is the first and the most excellent engineer you would find anywhere. Look at nature. Look at the things that he deliberately and precisely planned and designed. Look at the human beings, right? When you take, we were looking at what it took when at master's level, how to control a robot. We're dealing with robotic manipulators. There are different kinds of robots. You have mobile robots, you have robots, manipulators, those ones that are not mobile, and all of that. And manipulative arms, you'll find them in industrial setting where you have this mostly six degree of freedom robotic arms. They imitate the hand, right? You see them doing different things. They pick things, they place them, they cover things, they move things along production lines. They do all of that, but the control of that is mind blowing. For we human beings, it's very easy when you want to drink water, you will pick the cup, drink your water very normally and drop your cup, right? But we are not very much aware of what it takes, that you grab your cup with the right amount of pressure on the cup, that it doesn't crush. You know, you have plastic cups, you have metal cups, you have ceramic or glass cups, right? When you have a plastic cup that can be squashed, your brain knows that this is a plastic cup. And so it controls your hand to pick it up just with the right amount of force, just to pick and lift the cup up. All right. Then when you pick the cup, we pick it up at the right velocity. We pick it up at the right velocity, we bring it to our mouth, we accelerate a little bit, get to a velocity that remains constant, then we decelerate by the time it gets to our mouth. Okay, when it touches our mouth, we tilt the cup at the right angular velocity. Okay, that's control. Something is controlling all these parameters. The force, first of all, how wide you open your hand, the force with which you pick up that object, the initial velocity of yanking that object off a stationary position, the velocity with which you move it to wherever you want to move it, then how you slow it down, how you keep it down. All of that is control. And if you see the amount of equations and the amount of systems that need to be in place just to do something as simple as that is mind-blowing. It's mind-blowing. And that's why we always stand in awe of who God is, the brilliance that we find in nature. Man has almost everything man does and has engineered. He studies natural systems, right? And then uses them to implement in what he does. God is great. God is great. And if you are not following God, if you are doing your own thing, I used to be, God is just too much. And he keeps giving us, you know, little portions of this knowledge. All our explorations as human beings, all humanity, all that we've discovered. Science is just about discovering what God has already done. We only discover it when we're doing research, we're trying to find out. If you look at the process to establish a scientific law, you have to observe. You're observing something that is happening, then you will hypothesize, you bring out a guess. I think this is the reason why this thing is working like this. Then you go and carry out experiments. You try, vary a few things. Then you say, actually, you confirm that hypothesis and it becomes a law. For something to happen like this will happen, this will happen, this will happen. That's why we have laws that even govern our principles in engineering, our manipulation of the substances around us to meet our basic needs, to do basic things. Okay? So the first definition we will do is to define a system. So when we refer to a system, we're referring to a combination, right, or an arrangement of different physical components that work together as a single unit to achieve an aim. So fine, you want to which example would I give you now? You want water to flow in your house, right? You do not want to go to a well and fetch water. You will build a tank stand. That's one physical unit. You will put a tank on it, right? You will drill a borehole. You will buy a water pump. Okay, you will connect that water pump to a power supply. Okay, and then you connect the pump via piping systems to your tank. Then from your tank, you will you will have a piping system that takes water from the tank and distributes it everywhere in your building where you want water to flow, right? That's a system that does something that provides or distributes water, okay, into a building. It gets the water, so the water is pumped from a borehole. It stores the water in a tank, okay? But that tank does not only act as a storage system, it's also a distribution system, passive distribution. So it is elevated to some height, okay? And then that water is distributed to the various buildings. That's a system. Physical components have been arranged, they've been combined in a certain way. If you put your tank on the ground, water will not flow into the house. You will need to install a pump to push the water into the building. Okay. But to remove that pump, then you need to elevate your tank. It's a system, a deliberate arrangement of physical components in a certain way to form a unit that achieves a certain goal. Is that clear? Are you with me?
Yes, sir.
Good.
Yes, sir.
All right. So, control. What is control? Control, as the name implies, is that action, right, that commands, that directs, that regulates a system to get a desired outcome. So any action that does something to a system, it controls the system. It is a control. Is that okay? Then your components, that aspect of the system that is manipulated, that is regulated, that is controlled, that's what we call your plant or your process. Are we together? The part or component of a system that is required to be controlled, that is controlled. So for the case of the air conditioner, what is the plant? What is the plant? What is the part of that system that is being controlled?
The room, the air in the room.
The air in the room. So the air in the room is your plant. Is that okay?
So,
All right, let's move on. Your controller. So we've talked about control. Control is just the action, right? The action that manipulates your system. Now, the part or the component of your system, it could be inside your system or it could be external to your system. But that thing that controls the plant or that controls the process, that thing is called the what? The controller, right? Is the one that is pushing, is doing something to your plant to change its nature, to change its properties, to change something about it. Okay? Control system then is a system. We already defined a system as a deliberate combination or arrangement of physical components, all right, such that they work together as a single unit to do something. So a control system is a system. You have different things that are connected together, and its aim is either to control itself, okay, which means to command, to direct or regulate itself, or to control a different system to achieve a goal. So basically, a control system is a system that has a controller in it, because the controller is the component, the very thing that does the controlling, that does the regulation, the commanding, the manipulation of the plant. So a control system is a system with a controller in it to either control itself or to control a different system external to itself. Have we followed to that point?
Yes, sir.
So,
Yes, sir.
great. So, input, when we talk about input, we are referring to the signal or the excitation, the parameter that goes to the control system, okay, that gives the control system an information on what to do on the plant. That's your input. Okay. Most of our system control systems now are electrical in nature. So we find a way of changing a physical parameter into an electrical one. And what you find there is what we call a transducer or a sensor. Okay. Something, a component that will convert a physical parameter to an electrical signal. Okay, that signal is usually sent to a control system. Okay, and it informs the control system or it gives the control system information on what to do on the plant. So it is the signal or the excitation that is supplied to a control system, right? Your output is the response, the actual response that comes from the control system. So in all our calculations, we will represent vast control systems by equations. We will model them. Okay? Modeling is the process where you represent, there are different kinds of models. Now, I'm referring to mathematical models. Okay? When you come to your 500 level and I begin to take you what's it called now? Computer-aided drafting, and I'm teaching you how to use CAD systems. I'll teach you Autodesk Inventor, right? And we start talking about 3D models. Those are computational, digital, graphical models. So a graphical model, what we do in drawing, what we do in engineering drawing and engineering drafting is to represent a given component, a given concept, a given machine in in a geographical way so we can visualize it. Are you following me? Aha. So those models are different from mathematical models. Mathematical models are expressions, mathematical expressions that represent a physical phenomenon, a physical concept an event that happens in real life. Okay, all the equations that we deal with, and we'll deal with some of them here. Equations of motion, they are models of motion in real life. Okay, they take the parameters that are working, that make motion possible, and they build a relationship between them such that we can manipulate. So control systems, and that's why you will do a lot of maths. You will have equations that represent. Okay, so when you look at, for example, a cooling system, the AC, what the AC works on is a cooling system. There are many heat equations that you've done in your thermodynamics and you will still do now and you will do in your final year, right? Thermodynamics that says, look, the rate at which heat flows between two different substances depends on the temperature of those substances. It also depends on the boundary between these two substances, and it also depends on the thermal conductivity of these two substances, right? How easy is it? How much of the heat do they allow to flow through them? And then you have an equation that says Q dot, which is the rate of flow of this, equals the mass, the mass of that system, times a specific heat capacity, or which is a representation of the conductivity, right? Times the difference in temperature. That's an equation. So if you want a certain amount of heat to move out of a certain place, you can come and say, oh, this is the heat I want to go. So what do I need to do? What can I manipulate? That's what control systems do. So you bring an input that manipulates the system and you have your desired output. That's just one example. Is that okay? So your output is the actual response that is obtained from the control system. Okay, when the control system has acted on the input, then you have the output. Are we together?
Yes, sir.
Good.
Yes,
So
sir.
Yes, sir.
when we start looking at equations and all of that, you will understand what we're dealing with. I will show you when I define what a block diagram is. I will show you each of these. The next thing I want to define is a disturbance. So a disturbance, so far as the control system is concerned, is a signal that has a significant and an adverse effect on the performance of the control system. Okay? So, for example, we were talking about how do I get disturbance? When you have electric cables, right? And there is a magnetic field. So your electric cable, what you want your electric cable to do is to transmit current. It brings current from one place to another to do something, right? Or you could have a signal cable that is transmitting electricity, yes, but that electricity is representing audio sounds. So if you come to sound systems, we want to magnify a particular sound, or we want to transmit a particular sound from a given place to another. You will have a transducer. You have a sensor that can convert sound energy to electrical energy, and we call those ones mics, microphones. Okay? Your microphone is a sensor that converts audio sounds, audio energy, sound energy to electrical. Then that electrical signal is transmitted along a cable. Okay, sometimes we pass it through an amplifying system that will increase, it will increase the amplitude of the sound, and you send that, and then it goes to your. Somebody is unmuted. Please, can everybody mute themselves so that let me see who is not muted. Thank you very much, Abel.
We go see three for background.
Okay.
We go see three for
So
background.
when that signal is going along your cable, if there is some magnetic field, please make sure you mute yourself. Victor, you are unmuted. Can you mute yourself?
You know him that we show them.
Maybe I should mute to myself and then you won't be able to unmute yourself. Thank you. All right, so a disturbance, a signal comes in and distorts. So what you are hearing coming out of your sound, your speaker, is not clear, right? It's not clear. Something is disturbing it, something is affecting its performance. And that signal that comes external, it comes from somewhere else, and it affects the performance of your control system. That's what we call a disturbance. What we want, ideally, our control system should be isolated from every other signal such that it's only our input. What we send to it will determine what it brings out. But if there is a different signal that is able to access, is able to enter our control system and affect its performance, then it's a disturbance. Is that okay? So in designing control systems, you will get to a point where you have to design to, to isolate or to reduce the effect of disturbances. So when you look at audio, some cables, you see that the metal that comes in, there is something, there's an insulator around them, and then they have a shield, they have one metal thing like that, round that one, before you have your plastic insulation cable round. All of those things are systems that have been deliberately designed to minimize disturbances as your signal is passing in the cable. Okay? When we refer to automation, we are just saying that we are controlling a process automatically without human intervention. You don't have human beings that are there to continually give instructions and give, feedback to your control system. Your control system is programmed to act on its own. That's what we mean by automation. Okay? Without human intervention. Now, I talked about a transducer earlier on, an actuator. An actuator is that device, it's a particular device that causes your plant to change its parameter. So it takes action, okay, on the plant. It causes the process to provide an output, okay. And generally, they are mechanical devices that provide motive power to your process, okay. And so at the end, what a transducer does is it 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 reads your parameter, whatever your physical parameter is, it reads it and converts it to electrical signal. Now, when your controller has finished doing what it should do, it will send an output, which is also an electrical signal that goes to your actuator. Then your actuator will impact. It will cause your plant to change, to cause something to change in your plant, a parameter, a value, something, a physical quantity, as the case may be. So that's what an actuator is. It is a device that provides motive power to the process. Great. Feedback signal. Okay. A feedback signal is a measure of the output of the system that is taken and fed back, as the name implies. It is put back into the control system. So it will gauge itself whether it has achieved what you want it to achieve. Okay? So just the way feedback works in real life, we want you to do something, we give you the instruction, you go and do the thing. So we are waiting to hear from you. So when you come back, we say, what did you do? That's what you guys did during your IT defense, right? That's what you did during your IT defense. And oh no, it's not you guys, is a final year. That's what you will do. Let me talk in future terms. That's what you will do in your IT defense when you go on
Ika
IT
Ushu.
in 400 level, second semester, and you come back. Who is that person talking there? Fidelis Yolumun. Can you mute yourself? Maybe next time I will make sure that nobody can unmute themselves. No, not chat. I don't want chat. I want this. And I'm going to mute everybody. Allow participants to unmute themselves. No. So you cannot talk now. I'm the only person that is permitted to now talk. Great. Which means I cannot now get feedback. That's the problem. When I ask you a question, are you following me now? You can't give me feedback. Feedback, as we're explaining, is when you bring a measure of the output back to the control system. So it checks whether it is achieving what it should achieve. Okay? A negative feedback is when the output signal you are bringing in, and you will see this when we start doing calculations, is subtracted from the input signal so that the control measures the error. What is the difference between my input and my output? So usually the input is the desired thing we want. So that comes into the system works on it, and then we take the output and take it back. And so it makes a subtraction. If the output is the same as the input, then when you subtract the output from the input, you have a value of 0. Okay, which means that the error is 0, and so the control system is achieving what it needs to achieve. So negative feedback is when the feedback that is coming from your signal, we are subtracting it from the input signal to provide an error value in your control system. What's a block diagram? A block diagram is an arrangement of operational blocks, graphical blocks, that represent the transfer functions of your system. I will define transfer functions when I come to transfer function, but basically it's a measure, it's the equation that tells us what the controller is doing. It's the ratio of your output to your input. That's what a transfer function basically is. But it's not just an ordinary ratio. Okay, that's why I say this is maths. It's actually the ratio of the Laplace transform of the mathematical model representing the output to the Laplace transform of the mathematical model, that just means the equation, representing the input. All right. So when we create blocks that show us, these transfer functions and how they interact with your signals, your input, your output, and all of that, that's what we call a block diagram. Now, this is an example. This is an example of a block diagram. Okay. This is an example of a block diagram. So you can see these blocks. That's why we call them blocks. These are major blocks that represent transfer functions. Okay, your arrows represent your inputs and outputs. Okay, this circle here, we call it a summing junction, because so let's look through this. You have an input or a reference. Okay, it's a physical parameter in the environment. And then you have your input transducer, which is your sensor, okay, that takes that value, converts it to an electrical value, and it sends that to the controller, okay, to the controller. This whole block diagram is the block diagram of a control system. Okay, but this particular component, this particular part of the control system is the controller. In itself, it might be a subsystem. So you can even break it down and you will see other different units that are working together to control, right? But what it does is it will receive this signal, work on it, and output that output, okay? And send out that output. Now, this output is supposed to go straight and work on the process plant, or the processor plant rather, right? But if there is a disturbance, you see that there's a different signal now coming from somewhere else. It's not coming from our input. It's not coming from the controller, but it's going to affect what happens to this process plant or plant. What we want is the signal from the controller. Okay, for example, if we say send 5 volts to this, and there is a 2 volts coming from somewhere else, and the plant is actually now receiving 7 volts, it will behave abnormally. It will not behave the way we want it to behave because we wanted to send only what? 5 volts. Or if you are applying a force on a given object and you want that object to move a certain distance, and you figured out that the force you need is 0.5 newtons, and so your controller is sending that signal. We want 0.5 newton to work on this process or on this plant. But because of maybe um, environmental winds or something, there's another force that comes and acts. Then we have more than the 0.5 newton. So that plant, that object you want to move, will either move further than you expected because there is a disturbance. Okay, so when we represent all these transfer functions and show how they are connected one with another, we call this a block diagram. Is that okay? This particularly is an open loop system. When we come to the various kinds of control systems, we will define an open loop. That will be in our next class. Great. Now I will define what a signal flow graph is. Now the signal flow graph is quite similar. There's a form of it that is quite similar to a block diagram, right? But instead of just blocks that represent the transfer functions, we have this signal, this thing that shows us the particular functions. They are still, so this could still represent this guy, right? But instead of just saying this is the input transducer and writing out the big transfer function, we can represent it by a value. And it shows us the linear relationship between these things. Now, let's begin to do the maths, right? Your transfer function here, this G1 of S, this bracket S, have you done, let me allow you, okay, type in the comments. Let me not do that. Type in the comments. Have you done Laplace transform before? If you have done, type it in the comments. All of you can see my window. Yes, you have done it. Excellent. So it makes my work easier. I will not teach you Laplace transforms in this class. You only apply it. Okay, so but once you see this S, you know that we have changed something from one domain to the Laplace domain. That's why there's an S there. Okay, it has become a function of S. Is that okay? So that's a transfer function. Now, your output is usually a product of your input times what your controller is doing. So your controller is doing something to the input. It will multiply it, it will act on it so that it has an output. Oyiman is raising up his hand, so I'm going to allow you to unmute. You can unmute now.
So your network went down
My network.
at some point. Yes, sir.
Are you sure? Are you sure it's not your own?
You.
Please, any other person that can corroborate his story that my network, type it in the something. Did my network is not stable. I'm not, no, it's not me. Please, if you think my network is unstable, it's not me. Everybody's talking. Good. It's okay. My network has been stable. Not be me. Oh. And I deliberately looked for where my network would be stable today. Because if it were that first machine design class, I agree I was a problem. But today, I am not the problem. So check your networks. Sorry about that. And that's why we're also recording it so that I will make it available to you guys. You can listen back. Right? Great. So let's continue with our class. So you will see that the output from a given block in your signal flow graph, right, is a product of the input and the action points, what the transfer function of that particular unit. Okay, so the output that is called x2 of s is g1 of s times r of s, where r of s is your reference signal. That's your input signal. Okay, so it's more like a transducer reads that, and what is sending to the controller is now g1 of s times r of s. So when your transducer, when you get to your controller, if this is the controller, right, your G2 of S will work on what is coming in. So you see that what is going out of this guy, which we have called X1 of S, is a product of its transfer function and what is coming in. For him, what is coming into him is G1 of S, R of S. So you multiply that. That's why you now see G2 of S acting on what? G1 of S, R1 of S, which was the input. Then when you come to this guy now, the transfer function here is G3 of S. And what is being imputed is what is coming out of. So it's easy to see how these things are linearly connected and the relationships between them. That's what a signal flow graph shows you. All right. I should have put two different images so you will see another form of, maybe in the next class, I will show you a different form of your signal flow graph. Is that okay? You see all of these when we start dealing with different control systems themselves, and we start doing transfer functions of real life systems that we have. Great. Now, just one or two other things, and then we will end this class. The regulator. When you have a control system that what it wants to do is to reject disturbance effects. So its desired values are already fixed. Okay, the output of your system is fixed and you do not want disturbances. We call that a regulator. All right, and we have that a lot with systems. What some of you call what do you call those small things? You call it what's the common name? This small one, this one attached to fridges. Stabilizer. What we call stabilizers. Some of those are not actually stabilizers, they are regulators. What the stabilizer does is very different to what a regulator does. But the regulator, sometimes we have both stabilizing and regulating functions in one unit. So, well, maybe I should not blame us for calling them stabilizers. So what is coming in that the regulator wants to regulate should already have been stabilized. Your value should be fixed. If your control system is fluctuating, the value is going up, coming down, going up, coming down, then it is not stable. And we'll look at what we call compensating techniques. How do you stabilize? That's when you start looking at Nyquist plots and the body plots that show you when a system is unstable and when it's not stable and all of that. Okay, but when it's stable and we now want to regulate, we do not want external disturbances to affect it. That's what we call regulators. Okay, so it's a system where the main issue here is to reject the effects of disturbances. Last definitions is some of them. So when we talk about design here, we're saying that process where you are conceiving and you are inventing all the forms, all the parts, all the various aspects of your system as you want it to achieve a certain purpose. When we want to simulate, we are trying to create a model. First, we've derived a mathematical model, but we also create a digital model of a physical system, and then we manipulate it, we investigate it to see how that system will behave if it were in real life. That's what simulation is all about. When we talk about optimization, we are trying to adjust the parameters to get the best, the most favorable of the parameters that will be advantageous for our design. Then specifications, these are statements that explicitly state. We will come and deal with specifications even in control, even in machine design, because machine design is about design. It's just that you are designing mechanical systems. That's why it's called machine design. In control, engineering and automation, you design control systems. You can follow the same process. Okay, so specifications are statements that explicitly say what your device is meant to be and what it is meant to do. Okay, specifications. What it says precisely what your device is meant to be and what it is meant to do. If you do not have specifications, your device can be designed to be anything. Okay, if you have an air conditioner that can cool as low as 5 degrees Celsius, most of the ones we have can go only to 16. They can't go below 16, right? And then they can't go over 30. I think they also can't go over 30. Otherwise, they become a heater. All right. So you have air conditioning systems that are designed, and that's the specification. They say, build for me a system that can control the temperature of a room between 16 degrees Celsius and 30 degrees Celsius. Right? That's a statement that says exactly, explicitly what your device should do. All right. And with that, I have come to the end of this class. We will continue next class. So I am going to now allow you guys to be able to unmute yourself. I'm going to stop sharing my screen. And then when I come back to myself now, I will spotlight myself for everyone. Do we have any questions? You can now unmute yourself and mute yourself if you so desire. Do we have
No
any
question.
questions?
Sir, there's a question, please.
All right, there's a question. Is that
Sir, please,
Emmanuel?
yes, sir.
Go on then.
Sir, please, when you were talking about the Laplace transform, I think I was having network issues. So please, can you just come right, please?
No, I just confirmed that you guys have done Laplace transforms. So I'm not going to teach you Laplace transforms. I will only apply. You will do the
No,
math
sir, there
and
was a
tell me.
definition you gave.
Oh, the definition. No, it
Yes,
was
sir.
the definition of a transfer function. What a
Okay,
Laplace transform does is it takes a particular model in a different what do we call it now? In a different field, in a different space, and transforms it, brings it into the Laplace domain, in a different domain. So that's the Laplace domain, we call it S domain. And usually when we do a lot with frequencies, we say we are transforming from a frequency domain to the Laplace domain, and all of those are different domains. There's the time domain as well. That's where we measure things, in relation to physical time. That's the time domain. If we take, so for such things, there will be a function of time. So you will see such equations, you see x of t. For example, equations of motion, they are functions of time. We can take those and transform them. We carry out an operation on them so that we bring them into the Laplace domain. The frequency domain is actually different from the Laplace domain. When you want to go to the frequency domain, you carry Fourier transforms. Okay, Fourier transforms take you from the time domain to the frequency domain. Laplace transform takes you from the time domain to the Laplace domain, S domain. Is that okay? But I define transfer function as the ratio. Somebody is talking there. You guys, you will make our online classes very difficult. If you are talking in the background, then mute your mic, right? Okay, so I said a transfer function is a ratio of the output of a control system to its input, right? But it's not just an ordinary ratio. It's a ratio of the Laplace transform, right, of its mathematical expression to the Laplace transform of the mathematical expression of the input signal. Don't worry, when we come to transfer functions, we will define it, we will do it, so you will understand. Is that
All right,
okay?
thank you, sir.
God
Yes, sir.
bless you, Emmanuel. Any other question?
Not actually.
Say again.
Don't think so. Don't think
No
there's
question.
any question, sir.
All right. So very quickly now, let's evaluate. Is this workable? Can we have all our classes this way?
No,
Yes,
sir.
sir.
Sir,
Yeah,
yes,
I
sir.
think it's possible.
No, sir. No, sir.
No calculation online will not be possible.
Yes, I will support that one.
Who told you
Yes,
that
sir.
calculation
Let's
is not
have one
possible?
online, sir.
Who told you that
Sir,
calculation is
we
not
can't
possible?
continue doing this online.
And sir, we have a less number online. We're just 40 participants here on this call, and we have up to more than 60 persons in the class that are taking this
Okay.
course. So I think that's just a major challenge.
There are so many others joining their friends now.
Okay, so it's mixed. It's mixed. Some people there are honestly advantages and disadvantages to both methods. If we come to class, for example, we will not be able to record and you will not have it available, right? So I'm just there
Exactly.
and all of that. This has that advantage, okay? But we actually turned to this because of our we were not sure we'll find the class. If there is a class available, we will have it in person. Is that okay?
Yes, sir.
So for next week, we will check and see if, but for design classes, even design, I don't even know. Okay, if we find a class for design, the physical class, that's what I mean, then we may not need to do this. But if we don't, then we just have to continue because we can't be going around looking for classrooms. The advantage of this is, like I said, you can have this video later on. In fact, I'm even working towards I will start building up my YouTube channel. I will record my class videos, put them on there. When you come like this, you will go and watch the video first so that when we come to class, we are just discussing. But I've not gotten to that point yet. Maybe this would have been one of those methods I would have used to record the videos and all of that. But that it's fine. So it's mixed. Let's go that way. If by next week there are physical classrooms available for us, then we come to class. If by next week physical classes are not available, then we have to continue this way. Right?
Yes, sir. Yes, sir.
All right.
Yes, sir.
Yes, sir.
Thank you very much. I was thinking I should use this time and touch machine design that we couldn't touch, but I'm already tired. Well, how many minutes do we have? We have about 42 minutes. Should I do that or should we go and come back another day?
I think we should
You
come
need
back
to
another
rest,
day.
sir. Sir, you need
Yeah,
to
please, we'll
rest.
come back another day.
It's me that needs to rest.
Yes, sir.
Romanus.
You need rest, sir.
No, sir, it's not work here. That means to rest.
Let's continue.
No. Let's do it another
Sir,
day.
sir, another day,
Please,
sir.
we need to relax our brains
Let's
too.
do this another day.
Our master.
People, it's okay. Oh. If I don't complete the syllabus, it's not on me. Anyway, God
Yes,
bless
sir.
you.
No,
I will
Thank
I
you.
will
it's
make
better like that. It's better, sir.
all
Just complete it because next time we'll have a shorter time. Because if we do it like this, we'll go faster and we'll be able to do everything.
it's okay. We are in a democratic region, so somebody
Sir,
say
we
no
said
Yeah,
the
attendance.
online
majority carries
The
class.
the vote.
beauty,
Please, no
well,
attendance.
the beauty of online this thing, well, that's it's not too perfect because if there are 3 people to one device, then we won't know. And some of your devices are not named correctly. So when I get back the attendance, I'll be seeing something like iPhone, this person's iPhone, Infinix Hot, and we will not know who that person is. That's otherwise I already have my attendance. I know those who attended this class by their device names.
Yes,
So,
sir.
and by the way, you guys by now you should know it's your generation is techie. You cannot be joining either a webinar, a Zoom meeting, or Google Meet, whatever it is, and your device is not named properly. We don't know who is joining. If you go to some high-end webinars, they will not even admit you if your device name is not properly because we don't know who you are. You might be a hacker. You might be somebody that may come to disrupt the class or something. So you people need to be more techy. When you are coming into, change your name, change your device name. In that way, getting attendance is very easy.
Yes, sir.
It's all right. I know you people are excited about attendance because you think in your mind, people think that attendance equals marks. No be so. No be so. Attendance is only to help us know who was in class, so that when you fail, we can trace the reason for your failure. We say, no, why can he not fail? He was not coming to class, or this person came to class. So
Exactly,
what
sir.
was wrong? Then we start tracing. Okay, but if this person came to class consistently, there's effort. So what can we do? That's the whole essence of attendance. It's not for marks. So the way people will be getting excited for attendance, you better know why some of us take attendance. Anyway,
Yes, sir.
after every class, I will send you my slides. After every class, I will send you. But this particular one, I will not send it yet until I develop the whole thing and finish. Okay, I can't be sending you small stuff. All right.
Yes,
Somebody
sir.
is still talking without muting himself, and it's not me he's talking to. Okay. Is there any
Yeah,
other
well,
question? Can we
Thank
go?
you, sir.
Thank you, Emmanuel.
Thank you, sir.
All right. God bless you
Yes, sir.
all.
Yes,
See you
sir.
God
guys
bless you
next
too.
week by God's grace.
Amen, sir.
And I need to have a time before you go. Romanus is trying to arrange a time. I need to have a time I will also come with Victor Chingbeda. So we will talk to you guys about your IT. Is that okay? How to
Yes,
prepare for
sir.
your IT, what to look out for, and all of that. So
Yes.
let Romanus, you arrange with you, and then you will tell us when we can come. Okay. God bless.
No New Year gift.